So the previous examples invite us to move out or to move away from the traditional paradigm where what we have is a set of feasible solutions, which are those solutions you can put into practice. And there's a single criterion according to which you can decide which is the best of all those feasible solutions, because you have a KPI for each possibility, and you can sort all solutions and get the best and implement it. So that's a very straightforward approach that might work in some situations because there's a dominant objective and the rest are not that important. But this approach is kind of weak because although it's logical, it has some flaws. For example, very frequently, as we saw before, there is more than a single criterion, and choosing is not that simple. And second, decision makers are human and they are not that rational and that consistent. This is especially important when it comes to multi-criteria, because we might comparing different criteria, we might not be very consistent, and there are specific techniques to address this fact. So let's move on and see that decision problems have different features to have a broader picture of the complexity of how decisions should be made. When it comes to the decision maker, we can have just one, or we can have several whose different decisions interact with each other, and you'd rather have what your let's say opponent or the other players in the game, the other decision makers are doing, so that you take that into account to make your own decision. Second, when it comes to alternatives, you can have discrete options or continuous. And when you have discrete options, you can have a finite set of options or an infinite set of options. Okay, and in the case where we have a continuous space of solutions, like for example, how much money I'm going to invest in a series of projects, this is continuous, and the set of alternatives is at least theoretically infinite. You can also have one or several criteria, as we said, and these criteria might be quantified in terms of numbers of KPIs, or they might be qualitative. For example, the color of the car, when picking the one we prefer, is something which is qualitative. And finally, when it comes to what is the reliability of the information we have to make our decision, or the uncertainty, we might have deterministic context where we may assume that the data we have is reliable enough so that we assume that this is the actual data we're going to have, or we might assume a probabilistic nature of the situation, so that we can assign some sort of probability to different numbers that might occur, such as the demand we'll have to satisfy, or the cost we'll have in the future for our supply network design. Okay, so this is the whole, or quite a comprehensive framework where you can combine different options and you have quite different problems. We're going to focus here on one decision maker having several criteria in a deterministic context and having either discrete or continuous options. Because when we talk about multi-criteria, we are addressing the case where we have a small set of options, okay, and we want to choose one of those, okay, and we have different criteria to assess each alternative and different weights for different criteria, which to some extent it refers to the preferences corresponding to, or the weights for the criteria corresponding to the decision maker, because different decision makers have different preferences in terms of the different, or the relevances of the different criteria, and we have a different performance of each alternative for each criteria. And examples that illustrate this context or multicriteria are those three that we have here. When we have to select a supplier, we typically have several suppliers. We don't have thousands of suppliers to choose from, so we have a bunch of them, and we might compare them in terms, for example, of costs, lead time, and quality. And this might be in conflict and we might want eventually to pick the one that has a good combination of these three, but it's not that obvious to identify which is best one according to the context and the decision maker. Let's say make that consideration. This is a different concept of best. It's the one that satisfies our needs according to our preferences. Imagine we have designs among a set of technologies for our production process, and each technology has a risk. It's reliable or not to some extent, and it has different costs. So we have to decide which technology to go on with. We need to take this into account. Or, for example, we are defining a project. There are these classical three criteria that are in conflict, which are the scope, the cost, and the time. So we might go for a definition with a higher scope, but at the cost of having a more time involved and to have a larger budget and different combinations of all these three. When it comes to multi-objective, this is an extension of the optimization problems with one objective. Okay? Typically, what we have is several objectives which are in conflict. And we have a large set of feasible solutions, like the one with the routes. Imagine that instead of having to visit only all those, I don't remember, but 8 locations, we have to visit hundreds of them. So the possible combinations to visit them is quite larger. And there's a very big search space for us to find different solutions. And each feasible solution implies a set of value for the objective. So if we have to visit hundreds of customers, each set of routes will give us a cost and a customer service measured by the time customers have to wait for us to arrive, for example. And we need to decide which is best. And ideally, what we would like to do is to convert everything into one single objective, for example, money. So if we can quantify what is the cost of arriving later to a customer into euros, we can sum everything as a single objective. But this is not always possible. You cannot quantify it, but the decision maker can have an idea when comparing two solutions, which are different in terms of cost and the time that customers are arriving, or whatever two objectives we are dealing with. And these are 4 examples related to multi-objective. For example, when we are designing our supply chain network, we need to locate different facilities. So cost and customer service are in conflict. So the more facilities we locate, the closer we will be to our customers. So that implies providing them with a better service, but it'll have a larger cost. For example, in production planning, we might have different KPIs, like the total make span to produce the orders we have waiting for us to be produced. We have the work in progress and the labor we're using, and the cost. So these are KPIs that are in conflict. In inventory management, we have 2 costs to start with, which are the holding cost, which is the cost for just having a product stored somewhere, and the ordering cost, which are the costs related to placing a single order with our supplier. So if we place orders very frequently, we will have a larger ordering cost, because we are ordering very often, but we will place orders with less quantity, so we won't have that much amount of product in our warehouses, so the holding cost will be lower. So since these are costs, we can translate those two into money, so that would be not an issue. But we also can have the cycle service level as the probability of having it stuck out, and that is not that simple to translate into euros. So those three elements should be considered or can be considered in the context of multi-objective, the multi-objective framework. And finally, let's consider the portfolio selection problem, where we have a set of funds where we can invest, and we can invest different amounts of money, and each of those have a return and risk, and we have some rules to decide to how many funds we have to invest in, the type of funds we should pick, and so on. But these two things are in conflict. So probably if we want a large return, we should be willing to accept a large risk, and the other way around. So there's no way for us to try to get the an increase in return and a decrease in return. There are some limits there that we will see in the next videos. So comparing the two approaches, where we have multicriteria and multi-objective, we have here the examples. Notice that on our left we have decisions where the options to pick from are just a few. We don't have 1,000 technology alternatives to implement our production process. Whereas if we are locating facilities, there are theoretically an infinite set of possible locations where we can locate our warehouses. If we are talking, for example, in the context of Europe, or we have production planning and we have to decide the sequence of products or orders to be produced within our system. Well, this might not be infinite. This is not infinite, but the set of combinations of all the orders that are awaiting and how they are produced in different machines in our warehouse, in our workshop. Sorry, we have a larger set of combinations than the ones we have when we are picking a supplier or selecting a technology. And finally, to address this problem, we have different techniques specific for each of these two frameworks. One is the multi-objective set of techniques, where we have weighted objectives or goal programming or epsilon constraints that try to address the fact that we might take care of one objective and not let the others go beyond some thresholds. So we contain some objectives and we try to optimize the other one. This is the general idea behind that. And we have multi-criteria, where we have weighted sums, which is as it just says, we just sum all the the value we assign to every feature of every option, and we have a weight for each criteria. You just have a weighted sum. We have AHP, Electra, and Prometheus, which are more sophisticated alternatives that are intended to overcome the limitations of the weighted sums, which are quite a few. I won't get into details of any of these techniques in this playlist, and I will just finally move to what Pareto optimality means, because it's a very relevant concept in the context of multi-objective.